All right, good to go.
Okay. Yeah, so we'll be talking about the research we're doing at Secondmind on the GP side, and maybe highlight some of the differences we can see between what the limitations we think are for GPs and what the limitations people in academia see as the GP limitations. So the talk is organized in three sections. The first one is I present briefly some use cases for Gaussian process models. So yeah, and I will present the challenges from an industry point of view and give some examples and a brief overview of some of the research we've done for each of the challenge. Okay, so let's start with the use case for GP models. So the first one is to model a financial time series. So a common quantity that is looked at by a quantitative analyst is the log return, and you have an image of log return on your right. So these time series are very extremely noisy, and the noise is heteroscedastic. The noise changes over time, and there's a lot of noise and very little signal in the background. And the question we'd like to answer is what is going to be tomorrow's log return, and what's the mean value, and what's the standard deviation of the log return for tomorrow or next week. And yeah, and we found that GP models were very good for this type of signal. Another example is palette collection. So if you produce some goods, and if you want to use if you need pallets in order to transport those goods, a common thing to do is not to buy pallets but to rent pallets to a company. Then you use the pallets maybe like to ship your product to some retailers, and the company you've rented the pallets to is going to collect the pallets at the retailer location. So if you're renting pallets, then the practical question you face is how many trucks should you send to collect pallets at, let's say, I don't know, at a Tesco um, location. And the data is typically non-stationary. It's not observed directly because you don't know, even if you go to the Tesco, you don't know the exact number of pallets in there. The type of observation you have is I've sent, let's say, 5 trucks, and 4 of them came back with pallets, and the fifth one came without pallets because everything there was taken. So you just observe bounds on the quantity you're interested in. And there's some discontinuity in the signal because each time a truck picks some pallets, then you have a drop in the quantity of pallet on site. So this can be represented by a stochastic differential equation, and things are linear. The noise that drives the system, we can make the assumption that it is Gaussian. So we end up with another Gaussian process model. The image there is one example. So you have the the green lines and triangles show the successful collection. Sorry, so we know we have one truck that went there that collected 500 pallets when you have a green line, for example, and the red one. So that gives us a lower bound on the quantity of pallets, and the red one are the failed collection. So that gives us an upper bound on the quantity of pallets. And just given these bounds and the knowledge we have from our model that is given by the stochastic differential equation, we can make some predictions in the future about the number of pallets. And interestingly, we also have a measure of the uncertainty. So we can know the risk we are taking if we send one more truck or one less truck. And the last example I'll talk about is something we are working on very intensely at the moment. And that's an engine calibration problem where we want to calibrate the engine control units, the electronic control unit of the engine. So the ECU is a piece of software that controls the engine cycles, and it will use some sensor readings, for example, what is the RPM or these kind of quantities, and adjust some various engine actuators. So, for example, it will adjust when the valves should open and close, when do you inject fuel, all these kind of things. All those variables are controlled so that the engine runs the best it can. So that means such that the fuel consumption of the engine is as small as possible. So the data in order to find a good calibration of the engine control units is collected just by running an engine on test bench and testing different parameter configuration. So data is typically expensive to collect. It will be noisy and with heteroscedastic noise. It is often non-stationary. You can have cliffs in the objective. So like changing one parameter a little bit can, in some location of the input space, like imply big changes on the value of the fuel consumption. And another thing of this problem is that the input space, all the input space cannot be visited. There are some areas that are not safe to run the engine. There's a risk of damaging the engine in these for these parameter configurations. So, so there's some inputs that you cannot test, but you do not know in advance what are these configurations that cannot be tested. So yeah, so it's another type of problems where we fitted GP model, SVGP models like sparse variational Gaussian process models, and yeah, and fitted also models based on GPs, classification models in order to learn what are the areas of the space that could not be visited. And those models were then used in the Bayesian optimization loop. I didn't say it at the beginning, but if you have any questions, please interrupt. There will be like time at the end for questions. But if you want to ask questions down the line, I'm very happy with that. I cannot see the list of participants, so if you raise your hand or things like that, I'm not going to see it. But if you just jump in, I think that would work.
Alternatively, if you raise your hand, I can bring it to your attention.
Okay, brilliant. Let's do that. Thanks. Okay, so why are we that fond about GP models? So the first one is that they are great for quantifying the uncertainty. So we can control the risk that is associated with the decisions that will be made on top of the model. And this knowledge of the uncertainty can also be used to derive exploration trade-offs, like if you do Bayesian optimization, for example. The other thing is that it's a very versatile framework. So we can do models with non-conjugate likelihoods. We can finely tune the kernels. We can do many, many things to make the model well suited for a wide range of applications. There's also the fact that GP models are comfortable with both small and big data regime. If you have small data, then they can be very data efficient because your model also carries a lot of assumptions. So you don't make your prediction just using the data, you make your prediction using also the prior assumptions that are in your model. And in the low data regime, having good prior assumptions is a great way to get good predictions. But they can also cope with large data set, especially using like variational inference and sparse Gaussian processes. And yeah, and finally, the fact that it's a principal approach, like we know we can train the marginal likelihood as a training objectives, or that we can try to integrate over the kernel parameter doing an MCMC, but we don't really have like overfitting problems or all these kind of things with Gaussian process models. And maybe I'll finish the list with a bit of the dirty secret, which is we also like them a lot because they are mathematically tractable. If they were not mathematically tractable, I guess we would find another way to answer the questions I was listed previously. So I assume most people are very, very familiar with the GP regression. So this slide is more for introducing the notations that I will use down the line. So for a GP regression model, we assume that the input X and the output are related, as like the observation is the GP evaluated at X plus some observation noise that is Gaussian. We have an analytical expression for the posteriors. The posterior of the GP given the observations is still Gaussian. It has a mean and a covariance function that depends on basically matrix products and an inverse over matrix. And we can learn the parameters by the model parameters, so the kernel parameters and the noise variance by maximizing the marginal likelihood. We also use a lot sparse variational Gaussian processes. So for large data sets, the previous expression do not really work just because the covariance matrix that you have to invert are too big, or if your observation model isn't conjugate. So if the observation model is more complex than just Gaussian noise on top of the observations, then we don't have a closed form solution for the posterior. So an alternative approach is to try to find a Gaussian distribution that will be as close as possible to the posterior. And this as close as possible can be measured by minimizing the KL, the callback library divergence between from the approximate posterior and the true posterior. So a very common approach in sparse Gaussian process is to introduce some pseudo inputs that we will write Z and an inducing variable U that is Gaussian distributed, and to condition the GP with a pseudo observation. So say, okay, at the pseudo input Z, then I'm going to assume I observe the value UI, and I'm just going to optimize what is the value of Z, what is the mean and the covariance of U, so that my approximate posterior fits the true posterior the best way as possible. And this can be done by minimizing the elbow that is represented just there. Okay, so what are the challenges with these models? So I will talk about three of them. The first one is automation. So how can we obtain good model for a wide variety of data sets? The second one is compute. So how can we reduce the compute bills? And the last one is robustness. How can we prevent models from being very bad? Let's start with automation. So when we write a research paper, we have time and we have a bit of a chance to babysit the models so that they perform well. So we can do a bit of tuning, we can test different things and pick the one that works the best. This is part of the discovery process when we develop a new method. When you're working with a large number of models that may be deployed on the cloud and that maybe receive data on real time, like it's not really possible to do this handling of the models. So the type of questions that are interesting is, for example, data verification. How can I make sure that the model, the data that the model receives makes sense, and maybe can I use already an existing GP model to assess that the data I receive is good. Automatic selection is about how can we automatically find a good model for a given data set. And the last one is, can we have models that have lots of degrees of freedom so that they can adapt to lots of different data sets? I'm going to talk about the last two, like automatic model selection and flexible model in a bit more details. So I believe most people in the audience are familiar with the automatic statistician. So the idea is just to find a way to combine different kernels together so that we fit the data set the best way we can. And this combination of kernel can be summing the kernel, taking products of them, or introducing change points to have non-stationarity, but all these can be explored automatically. Another approach is to look at hierarchical kernel learning. So the idea is to have a kernel represented by a graph and to explore a kernel that writes as a sum of elements of this graph. So for example, if you take an ANOVA kernel, a kernel that writes as a product of a sum of a constant plus a univariate covariance, if you expand this product, you will have a constant plus univariate kernel plus bivariate kernel that are just the product of two of these guys, and we can. This gives us a very interesting structure, but we can refine this structure by saying, are there some element in this sum that I could get rid of? And that's what hierarchical kernel learning does. Like it starts with a simple covariance and try to find terms that could be added to the kernel in order to refine the covariance, but get something that is well tailored to the problem at hand. Another approach is not to try to combine covariances together, but just to start with a complex covariance in the first place and to try to optimize that all at once. Or just to start with models that have lots of flexibility. So for example, you could use deep GPs, or you can use kernels that are parameterized by their spectral density, or there's interesting work called a neural kernel network. So all these can make very flexible models. On our side, we've had some good result with importance-weighted deep GPs and spectral kernels built using blocks. I'm going to present briefly these two papers. So the importance-weighted deep GP, the idea is to have a deep GP model, but with an extra latent variable, like an extra input that is something that is noisy, and to use importance-weighted variational inference in order to learn this model and would be the value of the noisy latent variables. So this results in a model that can approximate multimodal distribution. So you can see that on the image on the right, like for one input X, like we can see two modes in here, for example, in the middle of the D, where the mass is split into regions. So this gives models some flexibility, and yeah, and it happens to end up with something that works very well on a lot of data sets. So this is the table of experiments in the paper. I'm not going to go into the too much details, but yeah, like for all these data sets, that's the exact same model that is used all the time, and there's like consistently a model that performs better than others, and it's a 3-layer deep GP with one latent variable and with importance weighted. So I would encourage you to have a look at the paper if you want to know more details about that. The Minecraft kernel is one work that will be presented at ISTAT in a couple of weeks. So we know that spectral kernels are good at capturing patterns in data sets. So the original paper was a paper from Andrew Wilson, where where the spectrum of the GP is modeled directly. So we look at the spectral representation of the covariance at the spectral density, and the spectral covariance is parameterized by a sum of Gaussian distributions, and that works very well. And this work is about extending this spectral mixture kernel into the multi-output settings, and we find that if you use Gaussian, you have some limitations on how much the different components can be correlated. So the method we introduce is to replace the Gaussian components that are used to build the spectral density by blocks, so hence the name Minecraft kernel. And with these blocks, we can show that we do not lose, like we can fully represent the correlations between the different outputs of the signal. So that's one way to build very flexible models, and because they have the flexibility of the spectral mixture kernel, but they also have a better way to represent the correlation for multi-output signals. Okay, the second big area I want to talk about is compute. So when we run a research paper, we have to run the experiment once just to produce the table of results. But in practice, when you deploy GP models, those are run continuously. Just because you continuously want to make predictions from the model, or you may receive new data online. So you'll have to retrain your model again and again. So if you have any inefficiency in the code, that will accumulate over time, and that will just make the compute bill grow quite a lot. Another thing that is, I think, specific to industry is backtesting. If you're making predictions on financial time series and making decisions from that, as soon as you want to incorporate a change in the model, the client will want you to backtest on all the history you have to date. What are the impacts of the changes you want to make? So if you have 10 years of history and you make daily predictions, it means you will have to fit like one new model for every day, and there's large cost associated to that. So the associated questions to reducing compute times are: what are the good practice when training GP models? And yeah, and maybe another thing is, as researchers, we tend to focus on the training cost, because what we do is train model and we use them to predict once. But in practice, like, prediction cost is also something that should not be neglected, especially if you use your model in a live environment. So what are a few practical tips I can share? I think an important one is to use good optimizers. Things like natural gradients are great, so that can make a big difference. I was having a discussion recently with engineers that were telling me that actually the choice of the covariance doesn't have much of an influence on the model accuracy, but the optimizer does have an influence on the model accuracy. And I can't believe that the choice of the covariance doesn't have an impact. I think it's just the choice of the optimizer is so important that it may look the choice of the kernel not that relevant. But I think that's just an indication of how important it is to have a good optimizer. It's not very surprising, but when models are updated sequentially, then it's much better to try to reuse the previous model as a starting point for the new optimization rather than starting from scratch. And the last one is that using all the data isn't always the right thing to do. So if you have a long time series, maybe just using the past 200 observations or something like that is fine. In some cases, so it's fine. So because it would reduce the compute time. But another advantage is that if your time series is not stationary, then you can end up with much better predictions just by fitting your model on the recent history, so that you're not influenced by what happened a long time ago that is not really relevant to describe your time series anymore. Yeah, so one of the research paper we published at IAStats in 2019 was on combining like Markovian Gaussian processes and variational inference. So for when you have the Markov property in a Gaussian process, so for example, if you use a Maten 1/2 covariance or these kind of things, then we know that the marginal likelihood can be computed efficiently. So this is what a Kalman filter does, or this is what a Gaussian Markov random field does. What happens in the non-conjugate setting, if you want to use variational inference, that it turns out that the same speedup can be obtained when computing the elbow. So how this speedup can be obtained? So the first one is that when you have a banded matrix, the choice key factorization is linear in the size of the matrix instead of being cubic in the size of the matrix. And when you have a GP with a Markov property, the covariance matrix is going to be a full matrix, but the precision matrix, so the inverse of the covariance, is going to be a banded matrix. Similarly, a triangle solve is something that can be performed linearly in the size of the system. And there's also a dependence that is quadratic in the bandwidth. So if you make the bandwidth equal to the size of the matrix, then you recover the usual complexity. So if you look at the evidence lower bound, sorry, and maybe one more thing on this slide. So using these two properties is something that allows us to basically have Kalman filters or Gaussian Markov random fields. So with these two properties, we can compute what is the marginal likelihoods in linear time for a Gaussian process. So what happens if you want to do variational inference? So if you look at the expression of the evidence lower bound, the first term here is quite easy to compute. Like there's nothing that cannot be done with the previous operators that were shown in there, but we also have to compute the Kullback-Leibler divergence. And if we assume that our inducing variables also have a bounded structure, then we end up with this quantity in here, KL, that we have to compute. We know that computing the Cholesky is something that can be done efficiently. So all these terms are not really a problem. The big one is this trace term, where we have to compute the trace of a product between a matrix that is full and a matrix that is banded. And it turns out that this can be computed efficiently using a sparse inverse subset algorithm. So we can still do variational inference efficiently. And if you look at the resulting time for like making a call to the elbow and or to the likelihood, we end up with something that is linear. So on this graph, we compare like a classic GP flow model where you need to invert the matrix, and this scales cubically. A Kalman filter implemented in TensorFlow is something that is going to be linear in complexity, and if you implement directly the linear algebra at the operator level in C and make that available to TensorFlow, then you have like again a linear complexity, but like with a coefficient that is much faster than what we have for things implemented directly in TensorFlow. And similarly, if we increase the bandwidth, the complexity grows quadratically, but like there's huge speed up that can be obtained. What I've presented above can also be applied to Gaussian Markov random field. So if your inputs are distributed on a graph. So here's an illustration for the Porto taxi datasets, which is a Cox process model with latent GPs indexed by the graph nodes. So the GP has a Markov structure. So Q is a bounded matrix, and the observations are a Poisson process with a rate equal to the exponent of f and the weight that comes from the length of the edges going to the node. So this is the kind of data that we observe. So that's the number of taxi pickup for any given node on the graph. And using this data, we can perform variational inference and derive what is the posterior for f. And we can see some areas like the downtown where we have more taxi pickup, and areas like highway in here where no one ever take a taxi over there. So another piece of work that we did along this line is to try to combine the sparsity we have from Markovian GP with the sparsity we have from sparse GPs with inducing inputs. And for a Markovian GP, if it's one-dimensional, we can basically see it as the solution of a stochastic differential equation, where we have some states that evolves over time, and the observation is just a projection of the states. And the idea of this paper is, instead of introducing inducing variables for the GPF, is to have inducing variables directly for the states S. So that means that when you have to compute your covariances between your inducing variables, then you can again use the Markov property. And if you want to compute the likelihood of the observations that you have in between your inducing variables, then those will only depend on what are the surrounding inducing variables. So that's another factor that allows us to make good computational gains. So here's an illustration with a Maten 5-half kernel. So in this case, the inducing variables is the GP value, the value of the first derivative, and the value of the second derivative. So those are represented in black in here, where you have the value and like a little, like this is represented as the Taylor expansion of the GP at this location. And in this, with these settings, then the elbow complexity, which is usually cubic in the number of inducing variables, becomes linear in the number of inducing variables. And these models can also be used as layers in deep GP. So that's one way to make deep GPs benefit from the Markov property. The last piece of work I'm going to present when it comes to reducing the computational complexity is an ICML 2020 paper from Vincent Dutordois. So this paper introduces a mapping between the data space and the sphere. So let's say your data live in a Euclidean space that is here represented as a line. Then we project all this. So we embed this data into a larger dimensional space, and then we project the data onto the sphere. And once the data is projected onto the sphere, then we can do all the modeling on the sphere before projecting our predictions back. And the convenient thing of projecting on the sphere is that for the GP on the sphere, we have we know what are the eigenfunctions of the kernel. We know what are the eigenfunctions of the GP. So we can use these eigenfunctions, which are the spherical harmonics, as inducing variables in a variational inference model. So this is interdomain variational inference, where instead of having like locations for the observations, we have a more complex inducing variable that accounts for the global behavior of f. And the main advantage from a computational point of view is that the matrix that captures what is the covariance between the inducing variable becomes a diagonal matrix. So that drastically reduces the cost of variational inference. And the approach is also very similar to variational Fourier feature, but it gives us a very nice ordering of what are the most important eigenfunctions we should consider. So what are the most important inducing functions we should have into the model? So VFF doesn't scale very nicely with the dimensions, whereas VISH scales very nicely with the dimension. So in a way, you can think of it a bit as a PCA model where we cherry pick what are the most important components we should put into the model, and our variational inference algorithm learns what is the approximate posterior distribution for these components that are the most relevant ones. Okay, and finally, I'll talk about robustness. So in research paper, the metric we look at are often what is the performance or accuracy of the model, and we want our model to perform best. In practice, when you try to make a business out of GP models, you are really interested in having models that perform reasonably well all the time. So you losing like a few percent of performance in the best scenario in order to gain a few percent of performance in the worst scenario is something that makes a lot of sense. So the practical questions are: what are the metrics that are the best suited for picking the right models? So how can we measure the robustness of a method? How can we monitor the health status of models that are running? And the last one that is very practical too is what are good fail-safe practice in case you have choice key errors. Some practical tips. So model initialization has a huge effect on the robustness. We use a lot multiple restarts. So we don't, we test at random a few configuration of the model before finding, then we pick the best one and we start our Gaussian descent from there. Another thing that we do, and I call that the Alan Soul trick because I've learned that from Alan, is for SVGP model, we first set the kernel parameters to a reasonable value, then we optimize over the variational parameters for a few thousand iterations while keeping the kernel parameters fixed, and then we optimize all parameters together. This is because when you initialize the model, you usually have a big mismatch on the variational parameters. So if you start optimizing everything at once, then you have a huge gradient on the kernel parameters, and you may end up in a domain of the space that is not good at all, and it's difficult to recover down the line when you optimize the model. Okay, and I'll just briefly mention this paper that is another paper from Vincent and people at Cambridge University. This is not yet on archive, but it should be there very soon. So the idea for this paper is to try to establish links between deep neural networks, or between neural networks and SVGP models, but between neural networks and the posterior of SVGP models. And one way to do that is to use activation functions like the ReLU as inducing variables for the model. So we use the same trick as like projecting the data onto the sphere, making the model over there and projecting back. But we do not use the spherical harmonics as inducing variable. We use projections of activation functions. And this is great to improve robustness because it allows us to initialize the mean of our deep GP models with deep neural networks. And there's been a lot of effort that has been put into what are the good practices to train DNN. And by doing this, we can benefit from all these good practices. Okay, as a conclusion, so wrap up. So the limitations that we see from an industry point of view can be different from the limitations we see as researchers. There are quite a few cheap tricks that can make a big practical difference. I've presented the one I believe we use the most. And yeah, the last one is that working on real life problems always trigger interesting research questions. So that's pretty much all I wanted to say today. The talk only covered our research on GPs, but like the other big area we are interested in the future is Bayesian optimization. So we also do quite a lot of research in this direction. We also put a lot of effort in developing like Python or TensorFlow frameworks like a GP flow for fitting Gaussian process models or 3S for Bayesian optimization. These two are open source, but there will be more to come in the very near future. And yeah, and finally, we'll open some research placement positions, I believe, next week. So yeah, stay tuned if you're interested. Thanks a lot for your attention. Those are the pictures I could find for the people who contributed to the papers or the team members we have at Secondmind. There's a few people I didn't have the picture, so I've just listed their name. I hope I've not forgotten anyone in this list. Thanks a lot for your attention, and yeah, I guess we have time for questions.
Thank you so much, Nicolas. Everyone, if you have a question, would you please just raise your hand in the Zoom, or if you don't have too many questions, just unmute yourself and ask. Right, Hong has the first question.
So I have a question related to importance-weighted deep GPs. You have latent variable that's treated as a latent variable and as an input to GPs. Do you have a prior on this variable?
Yes, there's a prior on the variables. Maybe the most, so the prior is Gaussian, and I guess the most striking fact is all these variables are supposed to be independent. So it's like white noise for these variables. And so for each observation, the assumption is that it has its specific draw of an independent Gaussian value. Does that answer the question?
Yeah, thanks. I also have one very generic question, but maybe I will leave this later and allow other people to ask questions first.
We have a question in the chat from Vessel asking, is this limitation of using Gaussian components alleviated by using more components?
Can the question be a bit more specific? Which components are referred to? Is it still in the importance-weighted case?
Sorry, this question, I typed it in the chat when you presented the Minecraft kernel.
Oh, okay. Okay, so okay, now I got it. So the limitations I outline is the fact that when you have Gaussian components, like inevitably their support is over the full real line, so the spectrum are going to overlap between two components, and this overlap of the spectrum is something that creates a link between the various components, but you cannot account for their full correlation because of this overlap in the spectrum. I'm sorry, that's not very clear, but the nutshell answer is if you take more Gaussians, you will still have an overlap between the spectrum, so you're still going to have this limitation that this overlap creates a limitation. If you are using blocks, then the blocks don't overlap, or you can split the blocks into smaller groups so that they don't overlap, and you can fully account for the correlations between them. So why the method works is not because we're using block, but it's because we're using basis functions that have finite support. Maybe that's one way to put it.
Okay, I think that makes sense. Thanks.
Okay, maybe I'll kick in my general question here. So you have done a lot of excellent work on deploying GPs, applying GPs to various data. In your view, do GPs have any downsides? I mean, if so, can we fix them with say reasonable amount of efforts, including computational efforts, or sort of innovations on the algorithmic side? Yeah.
Okay, so yes, the GPs do have limitations. There's things you don't do with GPs, right? And I think one way to look at your question is what is the what are the things that we cannot do with GPs, and if you want to do NLP, or if you want to do classification on images, these kind of things, they are better handled by neural networks, of course. If you want to, I don't know, some problems are very well solved with linear regression problems or these kind of things. So I believe each method has like its area of comfort. It turns out that the area of comfort of GPs is quite big, and there's plenty of problems where GP actually is the right tool. So they have limitations, and we are working on those limitations, like with the talk I just presented. But there's already plenty of problems where GPs, the way they are right now, are the right. It's just the right framework for tackling the problem.
Okay, thanks a lot.
I think Carl has his hand up to speak next.
Yeah, so I think this is a nice forum to explore the question about, you emphasize that if you're doing a research paper, then what you're trying to do is sort of slightly different from when you're creating a software product that you can actually sell, in the sense that you're allowed to sort of handhold the model in a way that you can't really practically do or afford in a sort of real world setting. I'm wondering whether you think that this problem will sort of go away in the future, in the sense that from an academic perspective, we don't really get excited about just fitting a Gaussian process to a new data set anymore, right? There has to be, we're using Gaussian processes to achieve various things within a more complicated setting, say within reinforcement learning or Bayesian optimization that you already talked about. So do you think there's a convergence? And with this convergence, would that be something that'll happen on a software level as well?
Yeah, so I think there's already some elements of a convergence. For example, the papers I presented from you with a very big table of results is not something that was motivated by an industry. It was like a researcher saying, okay, like we need to test the robustness of the method. We see more and more papers with extensive benchmarks, so that's definitely one way to make these things converge. I also think that the end goal will always be a bit different between academia and the industry, and things about like monitoring models that are running live. This kind of thing will, the need will always be more stringent in industry than it is in academia.
I think Andre had his hand up to say something.
Yeah, thank you. So my question is also a little bit maybe on the general side of things, but one of the things that GPs are often kind of praised for is that, unlike many models, they're able to provide you with some uncertainty estimates, which is probably a weird industrial setting where a lot of systems and people are not used to and are not really ready to consume this uncertainty estimates. They just want like point estimate. So do you have, in your experience working in Secondmind, do you have any, did you come across this as a problem, and did you find any practical ways to kind of deploy uncertainty to like in industrial applications?
That's a very, very good point. Yeah, so I believe like many others, we've struggled to communicate to some of our customers why this uncertainty was important when we were giving predictions, because it doesn't. We've tried various things. We try to give confidence intervals. We try to give like standard deviation around the predictions, this kind of thing, but it really doesn't help people much to make their own decisions. I think part of the answer on how to overcome that is that is not to provide directly a prediction that people can act upon, but to try to provide directly the decision ourselves. And then we can use ourselves what is the uncertainty in our predictions. And then it's also something where we can start speaking about risk, and people understand risk very, very well. So if you do not communicate on the prediction itself, but if you communicate on the decision you made based on your predictions, then it becomes much easier to talk about uncertainty and what are the possible outcomes.
Makes sense. Thank you.
I actually have a question on that note. One thing that makes GPs different from other models that communicate uncertainty is that the uncertainty between different points is usually not independent. So uncertainty about one outcome is probably, depending on the measure value of one outcome, the uncertainty in the other outcome could differ. I imagine this makes it more difficult to communicate the uncertainty to clients who are statistically trained. Can you comment on whether this is an issue in practice, and if your approach for this changes from what you just said?
Yeah, we haven't been into that level of details with our customers. We were just presenting uncertainty on point estimates, not the correlation between them. But that's a very good point. It would make things even more difficult to convey.
You might have to do a case-by-case analysis or something.
Yeah, but I also think like this this kind of correlation is interesting. Let's say if you want to if you're interested in the mean value or like if you're interested in the integral of a conditional sample, then of course you want to account for the correlation between the conditional sample at different location. But again, like you end up having like one criteria you're interested in, and you can talk about the uncertainty on these specific values. Otherwise, trying to be precise about the full conditional distribution, I think there would be very few cases where this is actually needed.
I think maybe without wanting to answer your question for you, I think the previous answer you gave is perhaps also an answer to this question, right? So if you think about the risk, or if you think about the consequences of making some decisions, then correlated error bars can certainly play into that. So in Bayesian optimization, for example, whenever you choose a new place to query the point, it's sort of obvious that you have to take into account that will inform the function not only at that point but at nearby points, and that has consequences for what's going on down the line, right? So representing the joint distribution of the entire posterior is, of course, it's highly problematic to visualize that thing. But thinking about the risk or thinking about the outcomes is actually, a simpler way to think about things, right? We'll mathematically, it'll refer back to the same thing, but maybe you shouldn't try to think about things in terms of those complicated distributions, but rather in terms of outcomes, and then you can sort of do whatever you need to do under the hood.
That makes sense. Thank you. Okay, I think at this time I'll stop the recording, but let's keep the discussion going with more questions. They just won't be published on YouTube. So thank you very much for your talk, Nicolas, and look forward to a nice discussion with you.